All right, good morning, everybody. Happy Wednesday. Hopefully, we're all doing pretty well today. So I guess for class for today, I'm going to go ahead and just continue from last time's content, which was I was covering those code snippet examples in C++ and trying to analyze at runtime. I do have a homework assignment up on Web Campus. I'll discuss the homework once I finish up this content, which is that code snippets in C++. So I'm going to just set up here. Let me see. There we go. Okay, I'm on the right spot, I think. Okay, perfect. So let's go ahead and start a screen share, and let's go and get into this. All right, so basically, what we're trying to do with these examples is we're trying to look at this code, and we're trying to count how many times it will run. So for the most part, we'll have several set of statements, which will be constant in runtime. So that cout hello world is a constant operation. Now, also to make one thing clear, is that I could have actually have done maybe 10 statements inside the for loop. Let's say I did 10 single C++ statements. That would also be just one constant operation. So it's because 10 statements or one statement asymptotically is about the same idea. So doing one is sort of good enough. But say if I did 10, it would be, let's say, it'd be 10n over here instead of just n. So it would still be linear in runtime. But basically, we're counting how many constant operations we're actually doing. That's basically how these things work. So let's go ahead and continue from this. Let me see if I'm in the right spot. I'm trying to find where in my notes we were currently left off. I think we can sort of go over nested loop examples. So these were the examples from last time where I sort of covered just one level of looping. So let's go ahead and now go over a nested loop example. So let's try this. So I'm going to try for int I equals 0, I less than n, I plus plus, for int j, 0, j less than n, j plus plus, and cout hello world. Okay, so for this one, typically students try to do the following, where they just basically just say, well, we have n times n, so n squared. And for the most part, that method is good. There are certain moments where that method might fail you when we do logarithms and so forth, but that's going to actually be good enough. But I'll go ahead and I'll show sort of the summation way of doing this. So first of all, you want to model the inner loop, which is going to go from j equals 0 to n minus 1. And we do this cout statement, which will be a constant operation. So the inner loop portion has the following summation: j equals 0 to n minus 1, and it's going to do this one statement. Or if let's say we had 5 statements here, let's say for example, then it would still be 1 because 1 represents a constant runtimes. Asymptotically, 10 statements or 1 statement, they're asymptotically both constant in runtime because this cout statement does not depend on the size of n. I mean, if n is larger, it'll output more times, but each cout statement itself, hello world, is not going to take longer if n is bigger. It'll do more outputs, but each output will take the same amount of time. So anyway, this will be our inner loop, and then here's our outer loop summation. Like this. So this sort of nested summation models this for loop structure perfectly. So you first want to compute the inner loop portion, which will be, well, we're going from j to n minus 1, so it's going to be exactly n number of steps. So we're going to add 1 n number of times to give us the value of n. So then our updated sort of summation looks like this. The inner loop, the inner summation evaluates to n. Now we're going to add n number of times right here, which will give us n squared, which will give us essentially O of n squared. So just to recap, in general, all these really are, in a sense, theta, but big O is good enough because I don't want to really get too complicated, but just like as I mentioned last time in class, I'm going to be using thetas on the exam, so that way you can't circle, something and still get it right technically, so that way there's only one answer for every question, but because these will actually run exactly n squared number of times, so it's really theta in a way, but big O is good enough. So anyway, so for these type of examples with nested loops, yeah, you could just multiply these n's like that and get a result n squared, but I wanted to show the actual sort of the step-by-step to how to get this result. So let's go ahead and try the following. Yeah, so j equals 0. So it's j equals 0 for all of these. So now for this one, let's try another example similar to this. How about the following example? So we're going to have 4 int I equals 0, I less than n, I plus plus, and 4 int j equals 0, j less than I, j plus plus. So a little bit different from the example above. We can imagine that this is going to take fewer number of steps than the above example. I mean, it sort of makes sense because the inner loop portion is going up to I, not up to n. So this example is similar to the one above, except it's less than I for j, so it'll be a little bit less. Let's see how much less it'll be. So again, let's go ahead and do the summation method to count how many times this hello world will get printed out. So we're going to say j equals 0 up to I minus 1, and then 1, which means you do one statement or a constant operation inside this for loop. And then, of course, we're going to nest this summation with this outer summation or loop like this. So the same setup as before. So then, let's go ahead and first work out that inner loop portion. And we have j equals 0 to I minus 1. We're adding up ones, so this inner loop will run I number of times. So if you go from 0 to I minus 1, then I number of steps it'll take. So we can go ahead and replace that with I. So you have I equals 0 to n minus 1 I. So this result, if we sort of, expand this, it's really 0 plus 1 plus 2 plus 3, and then plus n minus 1. Okay, fantastic. N minus 1, sort of like that. So, okay, that's great. So, I mean, we want to kind of generalize this into a formula of some sort so we can sort of know what's the asymptotic complexity of this. So basically here, in order to sort of answer this question, we have to kind of go into the past. So I guess to go forward, we have to go backwards sometimes, which is a very weird statement. But basically, so a long time ago, I think around 1700s-ish, I'm guessing somewhere around there, in Germany, there was sort of this instructor or this teacher who would sort of, I think it was a grade school teacher, I guess, he or she was sort of lazy or had not much to do that day. So I guess, the important part for the instructor is somehow make it to lunch or recess time So you have a break finally. So the best thing to do is when you're a teacher is have the kids do some work while you sit there and do nothing. That's always nice. So what happened was this teacher told these kids, okay, so exercise for right now is add numbers 1 plus 2 plus 3 up to 100. And once you finish that, you can go ahead and give me the answer, then you can go to recess. So naturally, you figure a teacher would sort of spend like a few hours because it would take a long time for the kids to finally get that done. But as one kid with the last name Gauss, um, after about a few minutes, went to the front of the class and gave the answer. It was 5,050 was the answer for that. And the teacher didn't know how this kid got this so quickly. And the trick was what this kid thought was, well, there's actually 50 ways you can add to 101. So you go from 1 to 100. You can have 1 plus 100, 2 plus 99, 3 plus 98, and so forth. There's 50 ways you can do that. So 50 times 101 gives you 5,050. That was the answer. So that works for 100, and it turns out this can be applied on any value. It could be for 1,000, for a million. It doesn't have to be 100. So general form for this is the following. So for this type of summation, we have add up 1 plus 2 plus 3 plus 4 like this. So the summation where I equals 1 to n, the summation will be n times n plus 1 divided by 2. That's that general form for this. If you plug in 100 for n, you'll get exactly 5,050. So we can go ahead and apply this formula. So I'll write this over here. This is Gauss's formula. We can apply this formula to this summation that we see right here. Let's go ahead and do that. So I'm going to, once again, write this formula out. So I equals 0 to n minus 1 I. Now I'm going to replace this I with a 1 because it's the same thing, because if you're adding 0 to our sum, it's not going to make any difference. So we'll just say 1 for I instead. We'll just remove that 0. So in this case, we're going up to n minus 1, not to n. So we're going to replace the formula with n minus 1 instead. So we're going to get n minus 1, multiply it by n minus 1 plus 1, divided by 2. So we simply just replace n with n minus 1. So we end up getting n times n minus 1 divided by 2 if we apply basic algebra here, because n minus 1 plus 1 will be just n, multiplied by n minus 1 divided by 2. We get n squared minus n divided by 2. So technically I was correct. This for loop, this version, is going to run less number of steps. So this for loop right here runs less number of steps than this for loop. However, not asymptotically less, because it's going to be n squared over 2 minus n over 2. So this is going to be just a quadratic formula. So this is going to give us the result of O of n squared. So we get the same result. So it's a little bit less, but not asymptotically less, just by some constant, or maybe by subtracting by n, but subtracting by n from n squared is not going to make the growth rate less than n squared. It'll still maintain that quadratic growth rate. So that's how we do that example. Let's see what else we have here. So I'm going to go ahead and just now talk about other examples. Let's go ahead and now incorporate logarithms into our summations. So let's go ahead, or into these nested for loop summations. Let's make sure I get the right one here. Okay, so for int I equals 0, I less than n, I plus plus, for int j equals 1, j less than n, j equals j multiplied by 2. And of course, our infamous hello world has to go right there. All right. So, in this case, well, let's see. So the inner loop portion, as we can see, we have j starting from 1 to less than n, and we double j each time. So the inner loop portion is going to just follow this definition of logarithms. So I start from 1 and multiply it by 2, double it each time until I hit n. That's going to take exactly log base 2n number of steps. So the inner loop portion runs log base 2 of n. So I'm not really quite sure how to model this by summation. That's just the definition of logs is sort of, how I was instructed to analyze this, or what I was taught when I was younger, I guess. And then I equals 0 and minus 1 because this outer loop is going to actually run n number of times. So we're going to sum this up. Now we can see here, we're going to add log base 2 of n number of times, which will give us n times log 2n, which will give us O of n log n. So that one wasn't too hard, really, because you're able to pick out that the inner loop runs log n number of times, and you run this n number of times. So again, not too complicated. Now let's go ahead and talk about this example, which will be a little bit different, but let's see, it's similar to this above example, but a little bit modified. Let's see if we can figure this one out. Oh, sure. So this inner loop portion starts off at 1, and we double it each time. So if let's say we have j equals n, and we divide it by 2 until we hit 1 or 0, we're going to divide by 2 log base 2n number of times. That's just definition of logarithms. If we start from 1 and double it every time until we hit n, we're going to multiply by 2 log n number of times. So it's just definition of logs. There's really no other explanation I can think of other than just how logs are defined. Yep. So over here, I'm going to now have a similar example like above, but a little bit different. So we're going to have I equals 0, I less than n, I plus plus, and here we're going to do the following. So j equals 1, j less than I. Well, that's going to make everything a little bit interesting. And of course, we have our infamous hello world right there. Okay. So this is sort of similar to that Gauss's formula example where we go to I instead of n. So this inner loop portion, again, we start from j equals 1 and we double it each time until we hit I. So it looks like we're going to have log base 2 of I number of steps in the inner loop. So we're going to have log base 2 of I, and then we're going to have a summation I equals, well, I'm going to say, we can say 0 and minus 1, but really we can't really have a 0 right there. So I'm going to first make this a bit more easier to read. I'm going to go ahead and just use 1 because there is no log of 0. It's not defined for logs. So we're going to go ahead and just use 1 just because, well, we can't really do anything else. It's the best we've got. So in this case, if we expand this, it's going to be log 2 of 1 plus log 2 of 2 plus log 2 and minus 1. So I'll just actually express it like this. So this is basically log 2 of n factorial. So I'm just mentioning this right now because we're going to refer to this statement or this formula or function in the future. So it doesn't really hurt to know that this summation is log n factorial, or maybe it's, I guess I want to be really nitpicky about it. This actually is going to really be log 2 of n minus 1 factorial, but it's asymptotically close enough to log of n factorial. So we'll assume that this is just about log of n factorial. So, okay, now that's great. So now we know that, but the problem is it's not really clear what this is going to actually give us. So we actually can approximate this summation using some other type of method. Let's go ahead and see how we actually do this. So we're going to, I guess, brace yourselves, but oh no. That's one of those weird calculus things right now. It's a calculus issue. I'm going to go up to 1 to n. Back to our old friend calculus again. So I'm going to have this go from 1 to n instead of n minus 1, just because make it simpler. So here we go. So this will be the last sort of calculus thing we'll do in this class, I think. Yeah, so there's the last one. So here we go. So to do this integration, we have to first get the antiderivative of natural log. Now, I chose natural log because really, remember, all the logs are off by the same, they're off by constant factor, but asymptotically they all have the same growth rate. So I can pick whatever base of log I want to fit the problem I'm trying to solve. So I chose natural log because we have a lot of work. So in calculus, there's a lot of work done with natural logs. So why make this any worse for us? So in this case, the antiderivative of natural log will be x natural log x minus x from 1 to n. So you'll learn this in statistics, actually. I believe that summations are sort of for discrete functions. Integrations are for continuous functions. So integrations also do sort of a summation on a continuous function. So we can approximate a summation using integration, which is kind of neat how we can do that. So, okay, so if you work this out, we'll get n natural log n minus 1 natural log 1 minus 1. So natural log of 1 will give us just 0 because for any log of 1 will always be 0. So we're going to end up with the result of n natural log n minus n, and then I guess plus 1 because minus a negative will give us plus 1. And, we can also use the following trick where the most dominant term takes over the entire growth rate. So n log n is more dominant than n or 1. So left off with n log n, or n natural log of n, which is, well, in the class O of n log n. So we got n log n with this as well. But I didn't want to just sort of tell you that. Well, I could have just said this, where believe me, this one actually is about n log n. Just believe me, ask anyone. I could have done that approach right there, and you'd have no choice but to believe me. But this way, just believe the math. The math doesn't really lie. I mean, it's right there. You can't really say, well, I don't know, Jimmy. I think it's not n log n. No, wait, what do you mean it's not n log n? I just showed you it's n log n. It's pretty clear it's n log n. So it's always good to have a math, proof. That way, there's no way I can get challenged in class because, it's right there. It's, case closed, mic drop, and that's it. So this example, technically, yes, we do get less number of steps like the above example. We get n log n minus n plus 1. But minusing n from n log n is not going to make a big enough impact on the growth rate. It will still asymptotically remain n log n. So it's a little bit less than the above example, but not asymptotically less is the key word. So that's that. Any questions so far? So I have 2 more examples left, and here's where things will get a little bit tricky. So here's where you want to be very mindful about these for loop examples because they can get a little bit tricky at times. So here's our last 2 examples. Then we'll go over the assignment 2. So int I equals n, I less than 0, I equals I divided by 2. So we see some logarithmic behavior, but be very careful if this logarithmic behavior is on the outer loop side, be very careful then. So we'll see in a second why. be very careful. So int j equals 0, j less than n, j plus plus. And of course, we'll have our infamous hello world. So only one more time after write hello world, so that's good. Anyway, hello world. Alrighty. So in this case, we're basically sort of having j's going from 0 to n. So what's going to happen here is inner loop portion is going to run, so I'll model this inner loop, j equals 0 to n minus 1, 1. And the outer loop is going to go basically from n, then we're going to have n over 2, n over 4, n over 8. So this is going to basically sort of model this sort of logarithmic behavior. So I guess I could put a summation here as well. This will be I equals 0 up to log 2 of n minus 1. I guess you could do that. And then, of course, the inner loop portion runs n number of times. So we're going to have the following at the end. So we're adding n log 2n number of times to give us n log n. So it'll just be O of n log n. I'll just sort of put that there like that. So this also gave us n log n as well. But whenever we have a nested loop and the outer loop portion has that log behavior, be careful because this could be a little bit of a trick. This one wasn't a trick, but this last question will be a little bit a trick. Let's go ahead and talk about this one, and then we'll be done with this, and we can go over the homework too. So for int I equals n, I greater than 0, I equals I divided by 2. So we have this logarithmic behavior again in the outer loop. And then we'll have our inner loop in j equals 0, j less than I this time. Oops. J plus plus. And then C out hello world. So this one basically is going to be a little bit different. So let's go ahead and work this one out. So in this case, we have our summation j equals 0 to n minus 1 I, like this. Okay, so my mistake, 1. So basically here, what's going to happen is this summation in the inner loop is going to run I number of times. And then here's where this summation is a little bit interesting. What's going to happen here is, well, I guess I'll just even do the whole thing at once. Actually, well, okay, fine. I'm going to go ahead and model the entire loop instead. So it's kind of hard to, I'm going to do the whole thing. So it really has the following summation. I'll just say n for right now. And it'll be n over 2 up to the power I. So it has this summation. So what happens is, I mean, just go ahead and just sort of in layman's terms say this. It'll first run n times, then n over 2 times, then n over 4 times, plus n over 8, until eventually we have 1 or 0. So this sort of summation models that perfectly. So now we'll have, I'll take the n out. I equals 0, and I'll say up to n for right now. And then we'll have 1 over 2 up to the power I. So this is going to follow the geometric series, and there's a formula that does this. So when we have a series like this, and the base of this exponential function, the base is less than 1, it's going to converge to a value. So the formula for this, you take the base, essentially, so you have 1 minus, so 1 over 1 minus the base of this summation, so like this. So there's a formula that does this for you. So 1/2 will be our base, so 1 over 1 minus that base value, which will give you 1 over 1/2, which gives you 2. So basically what this does is if I goes from 0 up to infinity, then it will converge to the value 2. So this summation can never be larger than 2. So if n is small, it'll be much less than 2. If n is very large, it's going to get very close to the value 2. So this whole summation will give us the value of 2. So I mean, we're going to substitute 2 because the idea is that it can never be worse than 2. Never can be more. So the max this can give us is 2. So we get essentially 2n will be our result, or the most it can possibly give us is 2n, which implies O of n. So this one gave us O of n. I'm going to zoom out so you can see both examples. Hopefully I can show both. But this one, if I have j goes to I, it's n. If j goes up to n, it's n log n. So this is the only one, I think, out of all of these questions, the only one that's kind of a little bit challenging actually is this one. Well, actually, that's not true. I could make this even worse. There's one example. I'm not going to show it. I'm not going to prove it, but there's one example that we also have as well. What about this one? I'm not going to really. So basically, so it is basically log 2 of n still, except that the problem's inner loop portion goes up to I, not to n this time. So it's still going to run. So this is going to be log a number of times still, but it models this summation instead, because j goes up to I, not up to n in this example. So we're going to run this log a number of times, but either way though, this pattern, this is going to be the rate at which this entire sort of summation grows. It grows based on this pattern, this summation. So it's still logarithmic, but the problem is that it grows like this. I guess, yeah, it's probably the best I can think of. It's kind of a weird question, so yeah, that's a very strange one. But it's the only weird one will be this one. So everything else I would imagine for the exam wouldn't be too hard, except this one is the real elephant in the room. This one's a little bit complicated. But I could make these problems in general worse. So here's one I could do. What about this one? I could do this. This one's much worse. Let me see some questions here. Well, I mean, it would be O of 2n, but remember, 2n is really just n, because that constant doesn't make a difference. So it's going to give us a summation of, give us a result of 2n, but 2n is in the class O of n. So this content is not really in a textbook, but I do have a PDF I typed up back when I taught 302 in the day, and I have this kind of worked out with summations and so forth, but I don't think this is actually in the book though. So an example would be just O of n. If it was theta, it would still be n, because theta n, because when I say exact for theta, doesn't really mean that it has to be exactly 2n. Theta n means it grows exactly at that linear rate. So it's still going to be n, even if it was theta, because it means that it grows exactly at a linear rate. So yeah. But I will post a PDF that has this stuff kind of typed up as well. So back in the day, I actually did this because there was one day, I think, my first taught this class in the summer. There was one day where students didn't show up because there was some type of crisis on campus. So I I had to type up the so I will post it up onto Canvas for sure. But anyway, this wouldn't actually be on the exam, this question, but I kind of covered something similar to this in my CS 477 class. This actually gives you O of log n. You have to use recurrence relations to actually solve this one, but it's O of log n, so log of n. So, but anyway, though, let's sort of not worry about this one. This wouldn't be really nice to put on the exam. You have to use recurrence relations and weird substitution tricks to actually solve this one. So let's sort of not worry about this one at all. Let's just move on. So I will post these notes up onto Canvas along with this PDF typed up version I have. So for the most part, you can work these ones out. The only one that's sort of bizarre is just this one. This one's a little bit strange. So I would just say, just for making this a bit easier to remember, if the outer loop portion has some log-like behavior, be careful. That could be a little bit of a trick. Everything else, though, should be fine. There's only one where it's like you could have a little bit of a problem if you're not careful. So these two are kind of similar looking to each other, but they're different. And log n and n are very different asymptotically. So yeah. So any other questions on this example or on these code snippets, for now at least? Alrighty, so let's go ahead and I'll just begin covering the assignment 2. I'll zoom in on this. Here we go, word ladder. So for this assignment, the phrase that words hurt actually could really be true in this particular example. Although I think this one's not going to be as hard as the assignment 1 because there's no linked lists involved. And linked lists are always something that is always fun for everybody. So there's no linked list here, but just recursion on this one only. So for this program, you want to compute the word ladder between two words. So word ladder basically is this definition right here in the write-up. Highlight this if you can see it. So word ladder is you have a start word and an end word, and you want to find words along the way where each word, so from start word to W1, W1 to W2, and so forth, they only have one letter different among them. So W1, W2, W2 has only one letter in that string where it's different. You want to find the words in that set, that series, that you can sort of go from the start word to the end word. So from the end word over here. So basically, I guess it defines it over here for you. So you only have to write one function in this one. So there's no classes to worry about. It's just basically sort of just one function you're going to have to write. You could write more functions if you want in this program, but you have to write at least this one because this function is going to be a recursive function. It's going to basically determine this word ladder. So in this case over here, we have bool word ladder, so it returns a boolean basically. So I'm going to go ahead and try to explain this in a second. So in this function, we're taking in a string word, and that first parameter is going to basically tell us the what word we're currently processing. And then the final word is sort of the, so from the start word, we're trying to get to this final word, basically. And then this const vector words is going to be our dictionary of words. So this program, you'll be given sort of this words.dat file, which you're going to read that in using a command line argument. And you're going to populate a vector with a bunch of words from that file. There's many words in there. So that's going to be all the words you're going to use in this word ladder. So, and then this vector string ladder at the very end, well, this is going to kind of maintain what words are currently in your ladder at the moment. So, let me see, I could discuss this more, but the problem is if I do that, though, I give away the answers. So there's not a whole lot to do in this function, actually. So what you want to do in this function, basically, is this. So so string word is the current word you're processing in this ladder. And you first want to check if that word equals word final, then you're done. That means you found a word ladder from that start word to that final word. Now, if it's not equal to that final word, what you have to do is you have to, well, go through every word in this words vector and find all the words that are one letter off from the word, yes, word. And then you have to go ahead and process that word. So what happens is, let's say you have the string word, and you find some string in that words vector that's one word off, one letter off from the original word. Well, then you're going to have to recursively call this function word ladder and pass in a different word into this function. Because all you're doing is you're on a current word, and you just have to go through your words and find one that's one character off. I found one, cool. I'm going to go ahead and recursively call the function on this new word. And then from that function call, it'll continue its process. So just keep on trying a word until it finally hits the final word, which means you're done, you solved it. Now, let's say you're on a current word and you tried every single word, all their one kind of character neighbors you found. You looked at all of them, and none of them lead to the solution. You have to back up to your previous function call and try a different word in that function call. So you're going to have a loop inside of this word ladder function, and you're going to recursively call word ladder within that loop, because the loop is going to look for a word that's sort of one letter off and call a recursive function on it. Then you return back to that function, and either it returns true or false. If it returns true, that means somewhere along the way it finally hit that word final. It found that ending word, which means now you just can back up all the way back to main. And then this ladder, this vector right here, is going to maintain the order of the words in the word ladder. So you simply output this vector at the very end in main. And let's say if you go back to the previous function call, and this returned false back to the previous function, that means if I chose that word, when I was trying to find a one character off word, it's going to basically say that from this word, I reach a dead end, so I have to go ahead and try a different word. So I have to basically, in my loop, just continue from where it left off and try a different word in that words array. And if I find another word that's one letter off, okay, cool. Then you go ahead and just call word ladder on that other word. And then same thing, then that function will halt and wait for a response to finally come back to it. If a true is returned back to it, that means, okay, we found, so somewhere down the line a solution was found. If a false is returned back, well, then you have to try a different word in that function body. So you're going to be looping to find a word that's one letter off from that string word. Really can't say more than that, because if I do, I kind of give away the answer. So it's really not a very hard program. It's actually one function, but I mean, it's not a very big program, but it's a little bit, maybe a little bit of a challenge, to think about this. So at some point, I have to return true or 1, but let's say it doesn't happen. Let's say there is no solution from the original words. Let's say, for example, for 2 inputs, there is no actual solution. Then it's going to return false for every single instance, and eventually it'll try every possible word ladder, and none of them reach a true. So then you return false all the way back to main eventually. So that's basically how you want to think about this. Yeah. So yes, you store the kind of the order in which you're processing nodes in the ladder, in this vector ladder. Yep. Well, I mean, I guess they don't have to, but in this example, all the words will be the same length. So they don't need to necessarily be, but Actually, they probably should, but either way, though, it's going to be the same size. So all the words will all be the same number of characters. So you can kind of assume that. So anyway, oh yeah, Labor Day weekend's right. Well, I mean, I kind of partially didn't ruin Labor Day by having the homework one be due Friday, but then I kind of partially ruined it. Or you can just yes, or you can work on it before Labor Day, take Labor Day off the weekend, and then just kind of work on after Labor Day. I guess you could do that. So that's always one option. I mean, it's not gonna be a giant. Like I think the linked list one was kind of a more of a whale of an assignment. This one's not going to be a whale really, but it's still maybe a little bit more complicated, but not going to be a giant program. So just to kind of practice using recursion. Something too bad here. Let me see. Not just a whale, a big shark. Assignment one be due on Monday? Hmm. I have to think about that because I mean I'm trying to think if that would just ruin our whole weekend then if I have homework one due on Monday. I'll think and see if that does work out well. So let me just think about that. Yeah, I understand. So definitely want to make sure you kind of get the whole linked list content. So I'll for now just kind of think about what I can do there. So that'll be the answer for right now. So I'm not saying no, I'm just saying that I'm just going to have to think to see how that will work out with the rest of my plans for the semester. That's all. So I'll think. Well, this one, the big notation could be exponential in runtime. This one. Because because it's going to essentially try a lot of possibilities. So it might be exponential. This one. So for this one, we're going to have written portion as well. So there'll be a few assignments in this class where I'll have to get written portion of an assignment as well because it's kind of part of the accreditation for the university. So as additional to having your assignment coded and running successfully, you want to also submit a written portion, preferably in some kind of PDF kind of form or a doc file. So Windows doc file should be okay as well. So I guess these questions, first one's kind of a straightforward one. But question two is an interesting one. Does this guarantee the optimal word ladder for given inputs? Optimal means the minimal number of words in that word ladder. So I guess the question is, if a solution exists between two words, does it guarantee the best solution? Why or why not? And then question three, I guess I kind of, in a sense, maybe answer question two with this, but when are you guaranteed to obtain optimal solution? Now, if you're always guaranteed optimal solution all the time, well then I guess just say that. But if you're not guaranteed optimal all the time, well what condition or what situation are you guaranteed to get an optimal solution for a word ladder? So I guess sort of think about these. So after you get your code done, just then, think about all of these ones. So you want to submit it to the code grade by deadline. So let's go ahead and check out code grade. Let's just see, let's take a look here. It has has like the output here as well. So I'll just go ahead and show you the output for this. Code grade. Oh, test student got got a perfect score on the on the um, on the auto testing part, huh? That's good. I'm good. I'm glad to see that. Yeah, I was able to get my own program to work. That's really awesome. Let me see. Okay, so basically, for auto testing part, it just compiles it. So you have to make sure your file is called assignment2.cpp. You have to also expect that you have to pass in your input using a command line argument, so words.dat. This fixtures part there is just a code grade thing, so don't worry about that. For you, it would just be ./a.out and then words.dat. But this you have to put this fixtures here because otherwise code grade won't be able to run this command line argument. But anyway, This is the output. So for the first one, the input is money and stone. So I want to find a word ladder from money to stone, and it's going to be this long output. So good thing it auto tests it. Now I have to see, because I believe there could be more than one possible solution. So I have to see how do I handle that if that does happen. So we'll get to that when we get there. But yes, the user will enter these two. Yeah, I'm just gonna scroll up here for a second. The user will just go ahead and just ask, you prompt the user, and the user will just type in money space stone, and then it's going to just compute the word ladder for that. And then for this input over here, chase and catch, and that's the expected output. So I guess my program generates this, enter word A and word B. I typed in chase, and let me see, where's the other input? I guess it doesn't really show it there, but at least it shows it here on the input portion. So it's chase and catch. And then this is the word ladder for that. You can see it's not exactly, doesn't seem very optimal, I don't think, but it does eventually reach the final word. There, see? It reached catch. Only after 553 letters or words in a word ladder, it finally reached it. And then I guess the sixth one, this is the case where it doesn't work. So the input here is angel and devil, which makes sense. That shouldn't work anyway, so it shouldn't be a word ladder for that. So this one actually produces there's no solution for this one. So the output would be, solution does not exist, and make sure you have it capitalized like this, or else CodeGrade will match it incorrectly. So make sure the casing is correct for that. So that's basically that. Actually, it creates more recursive calls than that, but it backs up to a previous word and then it will try a different path. So it's going to create more recursive calls than just that, actually. Those are the only ones that were part of our actual solution, but there are more recursive calls that could have reached a dead end, and it has to back up and try a different word, and it had to continue. So yeah, so it's exponential runtime, this example, I believe, or this code. So it's not optimal, really. And the output might not be very optimal either, but it does work. I mean, it's going to work. It's just, it'll take its sweet time getting there. So anyway, that's assignment 2. So this will be due next week. For now, homework 1 will be due, well, for now, will be due Friday, but we'll see what I can do with that. Yeah, so anyway, that's the assignment number 2. So I didn't want to say too much because I gave away too much of the answer, but really the recursive function is not very big. It's not really so insanely hard. So, I mean, it might be hard, but it's not going to be a big, mammoth of a program like the first one was, or a shark, or whatever you want to call it. So that's that. So to CodeGrade, just submit your source file, your C++ file, and also submit your written portion. That's going to count for your documentation. So let me go ahead and just show you right here. So for the most part, for a rubric, it'll always be just the program execution, the quality of code, which will be a number from 0 to 5, which is based on how close you were to your solution, and documentation. So that's going to be commenting. And also for this assignment, that written document will be part of this documentation code. So pretty simple for the grader to grade this, because really just pick a number based on how good or bad the solution was. So, and then this number will be out of 10, and that percentage will get scaled up to the points on Canvas, and then it should work. Hopefully it does work correctly. This is my first time using CodeGrade, but I try to keep CodeGrade simple. Just only test the output portion. Everything else, a human checking the documentation and quality is better, but the output part is really nice. I'll have to compile it manually and run them all and check that. So anyway, let's move on. So that's going to be assignment 2. So I still have some time left. So I guess we'll sort of now talk about a different topic. So I have my TA. I'm going to talk to her today during my break in my schedule, and I will ask her for office hours. I will concretely ask her. So that way I'll get her office hours, and I will post it onto, I'll update the syllabus on that. So I will definitely get that today, for sure. Yep. Yep. So, okay, here's a good question. So the input given, well, you can assume that the words will be in the word ladder, I believe. I think it should be on there. Let me just double check. Is Angel on this? Search for this. I think it should be on here. Yeah, so Angel and Devil are also on here as well. Angel and Devil are here as well. So you can assume that every word, the input from the user, those will be in the word ladder. And now just because they're in this words file does not mean they're going to automatically guarantee a word ladder solution. But input you can assume will be words that are in this file, words.dat. You can assume that. All right, so I guess now I'm going to go ahead and talk about a new topic. So our first kind of sort of algorithms type content. So I'm going to go over our first sorting algorithm, which is insert and sort. So before I go into insert and sort, I just want to talk about in general. Actually, wait. No, not sorting yet. Never mind. I'm going to go over searching first. Okay. Searching. Okay, fine. Yeah, probably good to start with searching first, actually. My mistake. I jumped a little too far ahead right there. Searching. So, well, searching is pretty simple. It's a process of trying to find some element in the list. So it's not really anything too bad. This will not be a very long sort of topic to cover, but let's go ahead and just talk about searching first. The very, very basics to any sort of data structures class is searching. So let's go ahead and write the following function. I'll call this find for right now. Then I'll have int, I'm just going to call this a, which will be the array, int n, which will be the size of the array, and then int s, which will be our search item. So I'm going to write our 135 sort of code that's used to find if s exists in the array. Let's go ahead and do that. Very basic stuff here. We'll have a for loop, so for int I equals 0, I less than n, I plus plus, then we'll check. So if a index I equals s, return true, which means we found the element, of course, and then we'll have this return false portion right here at the end. So, okay, there we go. Our classic searching mechanism from 135. So in this case, n will be the input size. So then, okay, so first of all, what's the worst case scenario for this find operation? Well, I guess one worst case scenario would be if this number s is not in the list. That would be one worst case scenario, obviously. Another bad case scenario would be, let's say if s happens to be the last element in the array. Now you have to go through every element until you finally determine that s is in the list or not in the list. So either s is not in the array at all, or s has to be the last element in the array, which means that s is not, or means s is in the array, but we have to go through n steps to finally reach that conclusion. So this runtime for this code is clearly going to be O of n. Because in the worst case, we will never go more than n number of steps. Now, of course, you could say, well, isn't this also O of n squared? Yes, it is. But once again, as I said before, that's a very weak statement to make if I say it's O of n squared. Because, yeah, it's correct, but it's, not a good statement, not a good thing to say, really. So O of n is the proper result because it will run n steps in the worst case. So the input is going to be given to us in such a way that's going to force this algorithm or this code to run the most number of steps. So in the worst case, this will never exceed n steps. So it's O of n. So now that we kind of understand that for loop code, we're going to be going over different algorithms. Either I'll give you the actual code or give you pseudocode, and we can sort of try to figure out the number of steps. Now in this one, we don't really go over lower bounds too often, but I'll do one example here. What's the lower bound for this problem? So just to kind of recap this, big O does not mean worst case, or it does, but it's not that big O is worst case and big omega is best case and theta is average case. No, the worst and best case depend on the input only. So in the worst case, what is the least you can possibly do? So once again, what if the input is given to you where S is not in the array, or S happens to be the last element in the array? Then that means in the worst case, you have to at least do n steps. It means that in the worst case, you have to at least do n steps because once again, if S is not in the list, or S happens to be the last element, that means even the minimal number of steps you have to do is n, because in the worst case, you have to do at least n steps, which means that this find function really is theta of n in a sense. But we'll just go ahead and keep the O of n part instead. So this code here is known as linear search, which makes perfect sense because the runtime is linear with respect to the input size. The input size will be n, and the runtime will be n. So it's linear number of steps. So that's our first searching algorithm. Not too hard because, well, we only have one level of loop. And these parts right here, these two statements inside of this for loop, well, these are actually going to be O of 1. They're constant because the if statement right there, this does not depend on how big n is. Because checking if a of I equals s, whether n is a billion or 1, that's not going to make that part faster or slower. Returning true is also not going to make the code, returning true is not going to be slower if n is bigger. That does not depend on n whatsoever. So that portion right there is constant, and we run this n number of times. That's our first sort of algorithm. Very elementary. And it's going to be O of n. And, and also the lower bound will be omega n. But for the most part, though, when we cover different algorithms in this class, we're not going to really go over omegas too often. I just wanted to just show omega, but for the most part, just remember it's O of n, linear search. So that's our first basic algorithm. Now let's go over our sort of next searching algorithm. So basically, we can do a different searching method if the following condition is met. So what if the list is already sorted? So the best way to think about this algorithm is, well, let me see. I guess, gathered around kids, old man Jimmy is going to discuss something from back in the day. So when I was younger, on Saturdays sometimes, we'd have a book placed in front of our door. It was a phone book. Now, what's a phone book? Let me go ahead and explain that to you. A phone book was basically just a book that was like, this thick, and it contained all the people that live in your area, and it has like their first and last name and their phone number. So if you wanted to, prank call random people, you actually could do that. Not that anybody would ever do that back in the day, but if you wanted to prank call people, that was very easy because you just had their phone number right there. So anyway, so the idea of the phone book, or even another relic, another ancient relic as well, is a dictionary, an actual book about this big, and it has all the words in English language with a definition associated with it. I know it's really weird. We had those back in the day. So same idea. If you want to find a word in the dictionary, or if you want to define a person's name in the phone book, of course you can open up the first page and go through all those names, and then next page, go through all those names and try to find Sarah Connor, like in Terminator 1. You can do all of that. But a better way of doing this is to break the book in the middle somewhere, or dictionary or phone book and check on that page what name do you see. So let's say, for example, I'm trying to find a person with the last name Jones, and I open it up and I see Hernandez, so H-I-J, so of course you have to sing that alphabet sound to yourself, H-I-J, so J is after H, so that means if Jones is in this dictionary, or in this phone book, sorry, that means Jones has to be on the right half, because I see Hernandez right there, so Hernandez's age is before J, so Jones has to be somewhere on the right. So all the pages to the left of Hernandez can be eliminated, because we know Jones cannot be there if this book is already sorted. So we try to break that part in half again, and we keep doing that until eventually we find that name in the phone book. So that method is much faster than trying to go through each word name one by one like that. So let's go over this dictionary or phone book search, or also known as a binary search, but I'll just go ahead and just put this here as a bool find. This will be binary search, however. I'll write this later on. So int A, int N, and int S. So anyway, once again, so we're going to have these variables. So int L, R, and M. So L and R will be our endpoints, and M will be the middle value of those endpoints. So L is going to be 0, and then R is going to be, I believe, N. So this might not be completely correct code in a sense, but it'll be good enough. And then, let me see here. M is going to be L plus R divided by 2. This might be a bit off maybe, but I'm going to go ahead and just, so basically this M is going to compute the middle of L and R, whatever the middle index between these two. So I'm not sure it's the correct way, 100% correct way, but I'm going to go with this. If it's not correct, well, basically I'm just saying M will be the middle index between L and R. That's what I'm trying to do over here. Then I'll say, actually, I can compute this later on. My mistake. I can compute this right here. I'm going to go ahead and do this first. So while L is less than or equal to R, I'll compute the midpoint here actually. So I'll say L plus R divided by 2. Then I'll check. So if A index M equals that search value, well, that means you found the element. So we can return true right here. We found it. Now, if it's not a match, well, you want to see, is A of M larger or smaller than S? So if A of M is less than S, that means S is larger, so S has to appear somewhere on the right side, because A of M is I broke the book in the middle, and S is a bigger value, which means that S, if it exists in this list, it must appear on the right side. So I'm going to shift L equal M plus 1. So L and R are my endpoints. So let's say if S is larger than the left endpoint, which I guess is kind of mirrored here on the camera, but it's going to just shift the endpoint up a little bit. So now we're going to have a smaller range we're looking for, because everything to the left of L is eliminated, because we know S can't appear anywhere to the left of L because S is larger than A of M. And then for the else case, so S is less, that means R will set to M minus 1, which will shift that right endpoint right to the midpoint. So everything after M cannot be, so S cannot be anywhere after R if S is smaller than A of M. S has to appear somewhere on the left of M. So we're going to shift that R index over to equal M minus 1. So everything to the right of M is now eliminated from our search. Then I'll close this loop up and return false at the very end. So at some point, if it's not in our list, what will happen is that it's going to basically, at some point, once L and R. Once this is not true, this condition, that means we tried every possible, we kept on trying. And once R is less than L, that means we know for sure that there's no way this element can possibly exist in this list. This will be known as a binary search. And then its runtime is going to be, well, let's take a look at this. So all the work in this while loop is going to be constant. But really, what happens is L and the R's keep on updating. And we divide this range of L and R in half each time. So we're dividing by 2, until we finally hit a range that's going to be, size will be 0. So this behavior is logarithmic. It's O of log n. So this method of searching is much better than linear search. But the problem is that if, let's say, this list is not sorted, you can't do binary search. So actually, it's not going to be worse than log of n, then no, it will not work at all. If it's not sorted, you can't make the assumption that, well, if S is bigger than A of M, okay, then obviously S must be on the right-hand side of M, to the right side of the list. Well, that's not true if it's unsorted. So if it's sorted, then it will work. If it's unsorted, this will not work at all. Whereas linear search works no matter what. Whether it's sorted or not sorted, this will always work. This only works if it's sorted, but it has a better runtime. In the worst case, the runtime is better. So the worst case, linear search is O of n. The worst case for binary search is O of log n. Now the best case for both of them is actually O of 1. So it could be where the first element, we found the element, we're done. But that's pure luck. So in the worst case, and typically for algorithms, the worst case and the average case is about the same usually. So really in the average case as well and the worst case, this will be O of log n for binary search, O of n for linear search. I guess I'll discuss this more next week. So I guess not Monday, but on Wednesday, we'll go ahead and continue on this. So for right now, take care, stay safe, have an awesome long weekend, and I will see you guys on Wednesday. Thanks for watching.